Good morning, all of you. Today I am going to make an audio recording for visually impaired student of organic chemistry book. Name of the chapter is Carboxylic acid. Introduction. Carboxylic acids are acidic compound having one or more carboxyl group C double bond OH or C double bond OH in their molecule. The name carboxyl is derived by the combination of the term carbonyl and hydroxyl since the group may be looked upon as the combination of carbonyl and hydroxyl group. The carboxylic acid are classified as mono, di, or tricarboxylic acid according to the number of carboxyl group present in the molecule. Thus, monocarboxylic acid may be represented as RC double bond OOH, where R may be simple or substituted alkyl or aryl group. However, the properties of carboxyl groups are essentially the same irrespective of the aliphatic or aromatic nature of the group attached to it. Nomenclature. First, common system. The aliphatic monocarboxylic acid are commonly called fatty acid as many of them, particularly the higher member, occurs in natural fat. The common name of the individually fatty acid are derived from some of their natural sources. For example, formic acid is so named it was originally obtained by the distillation of ants. Similarly, acetic acid derives its name from acetum in which it is present. Branch chain acid having only one branch of methyl group farthest away from the carboxyl group are named by adding the prefix iso to the name of compound straight chain corresponding straight chain acid. For instance, CH3CH, CH3, CH2C double bond OOH is known as isovaleric acid. Other branch chain acids and substituted acid are named as appropriate derivatives of straight chain acids, the position of the side chain or substituent group being indicated by letters alpha, beta, gamma, etc. Aromatic acids having the carboxyl group directly attached to the aromatic nucleus are generally referred to as derivative of benzoic acid. For instance, parachlorobenzoic acid is known as parachlorobenzoic acid. Some of these acids are however also known by special name as for example methyl benzoic acid are generally called toluic acid. Second is the IUPAC system. The IUPAC names of carboxylic acid are obtained in accordance with the general IUPAC rules, the suffix used for carboxyl group being oic acid. For naming open chain carboxyl acid, the name of the parent hydrocarbon corresponding to the longest possible straight chain in the molecule is written. The final E of this name is replaced by oic acid and the word acid is added. In numbering the carbon of straight chain, the carbon of the carboxyl group, which is present at one end of the chain, always get number 1, while side chain, if any, get other substituent number. For example, we have CH3CH, CH3, CH2C double bond OH is named as 3-methyl butanoic acid and CH3 single bond CH, double bond CH, single bond CH, CH3 single bond C double bond OH is named as 2-methyl pent 3 enoic acid. Carboxylic acid having a carboxylic groups attached to a alicyclic ring are named by adding the suffix carboxylic acid to the name of the ring. The carbon atom of the ring carrying the carboxylic group is always taken as number 1. For example, cyclohexane carboxylic acid, cyclohexene has 2 in carboxylic acid, 3 is 3-chloro cyclopentane carboxylic acid. The simplest aromatic carboxylic acid is benzoic acid. Other aromatic acids are named as derivative of benzoic acid. Salt of carboxylic acid are named by writing the name of cation followed by the name of acid in which the ending ic acid has been replaced by the ate. For example, sodium acetate, ammonium butyrate. Structure of the carboxyl group, acidic character of carboxylic acid. Even though the carboxyl group is generally represented by the structure C double bond OH, actually it is resonance hybrid of the following contributing structure. However, there is a separation of charge in structure second and it is less stable than structure 1. As a result, these two structures do not make equal contribution to the resonance hybrid, contribution of structure second being much less important than that of 1. Consecutively, the resonance energy is quite low. It is evident that in the resonance hybrid, oxygen of hydroxyl group carries some positive charge. As a result, the electron pair of the OH bond is largely displaced through oxygen. Due to this displacement of electron pair, the hydrogen of OH bond can be released as H positive ion with the simultaneous formation of the carboxylate ion. This is responsible for acidic nature of the carboxyl group. Now, the carboxylate ion formed by the ionization of carboxylic acid is also a resonance hybrid as shown ahead. It can be easily seen that the two contributing structure of carboxylate ion, third and fourth, are equivalent to each other and therefore they make equal contribution to the resonance hybrid. As such, the resonance energy of the carboxylate ion is much greater than that of the acid itself, for which the contributing structure differ considerably in their energies and do not make equal contribution to the resonance hybrid. In other words, the resonance stabilization of carboxylate ion is much more than that of the carboxylic acid. This greater stabilization of carboxylate ion tends to push the equilibrium in the ionization process through the right side and thus constitute the major product in the dissociation of carboxylic acid. Since the carboxylate anion is a resonance hybrid of two similar structure third and fourth, it may be visualized as equivalent to structure fifth. This means that the negative charge is evenly distributed over both the oxygen atom. Both the carbon-oxygen bond are equivalent and each is intermediate between single and double bond. This depiction of the carboxylate anion is confirmed by the X-ray diffraction studies of both of bond length of carboxylic acid and their anion. For instance, it was found that in the formate ion used in the form of sodium formate, both carbon-oxygen bond length have the same value 127 picometer or 1.27 angstrom. This is possible only if both carbon-oxygen bond of the ion are exactly equivalent. On the other hand, formic acid gives two different values for the carbon-oxygen bond length 123 picometer or 1.23 angstrom for carbon double bond oxygen length and 136 picometer or 1.36 angstrom for carbon and hydroxyl bond length. This shows that in formic acid the C double bond O has greater double bond character while COOH bond has greater single bond character. Orbital structure. The resonance in carboxylate ion can also be understood in terms of the molecular orbital concept. In terms of this concept, the carboxyl carbon atom is in the state of sp2 hybridization. These hybrid orbitals are directed toward the corner of a triangle and lie in the same plane at an angle of 120 degrees with each other. These three orbitals forms three sigma bonds, one each with a two oxygen atom and a third with an alpha carbon atom or hydrogen atom in the case of formate ion. The remaining unhybridized p orbital of the carbon overlaps sideways with the p orbital of both the oxygen atom to form a delocalized pi molecular orbital. In other words, the pi electrons are not confined to the nuclei of two atoms but get distributed around the nuclei of three atoms. This delocalization of pi electron led to the stabilization and ease of formation of the carboxylate ion. Comparison of acidic character of alcohol and carboxylic acid. Both alcohol and carboxylic acid contain OH group in their molecule, but alcohol are practically neutral compound while carboxylic acid have acidic character. This is due to the fact that carboxylic acid contains C double bond O group attached to the OH group. This enables both carboxylic acid and carboxylate ion to exhibit resonance, with the latter being more stable than the former. As a result, carboxylic acid get dissociated to form H positive ion and carboxylate ions. On the other hand, neither alcohol nor alkoxide re-exhibits resonance. Therefore, they do not dissociate to an appreciable extent and they are practically neutral in character. Comparison of acidic strength of phenol and carboxylic acid. Carboxylic acid are stronger acid than phenol. This can be explained in the term of stabilities of carboxylate and phenoxide ion. On comparing the structure of carboxylate ion and phenoxide ion, we find that the negative charge on the carboxylate ion is dispersed over two oxygen atoms, while in phenoxide ion it is present on one oxygen only. The charge dispersal on two oxygen atoms led to greater stability and therefore greater ease of formation of carboxylate ion. Therefore, carboxylic acid can release H positive ion more easily and are stronger acid than phenol. General method of preparation. The important method of preparing carboxylic acid are discussed below. First is oxidation of primary alcohol or aldehyde. Carboxylic acid can be readily obtained by the oxidation of primary alcohol or aldehyde. The usual oxidizing agent employed are acidified potassium dichromate, potassium permanganate, or nitric acid. Primary alcohol or aldehyde in the presence of oxygen give rise to carboxylic acid. For example, isobutyl alcohol in the presence of K2Cr2O7 H2SO4 give rise to isobutyric acid. Benzyl alcohol in the presence of K2Cr2O7 H2SO4 give rise to benzoic acid. Aldehyde can be oxidized to corresponding acid even by mild oxidizing agents such as Tollens reagent. For example, aldehyde plus Tollens reagent give rise to RC double bond O negative NH4 positive plus 2Ag plus H2O plus 3NH3. On further reaction of RC double bond O negative NH4 positive with H positive ion give rise to carboxylic acid. This method is highly selective as it would not oxidize any other oxidizable group such as alcoholic group if present in the starting aldehyde. Oxidation of alkyl benzenes. On heating alkyl benzenes with the oxidizing agents such as acidified potassium dichromate or acidified or alkaline potassium permanganate, the alkyl side chain get oxidized to carboxyl group. The reagent commonly employed is alkaline potassium permanganate. This constitutes a useful method for the preparation of aromatic acid as the alkyl side chain is always oxidized to the carboxylic group irrespective of its size. For example, alkyl benzene give rise to benzoic acid on oxidation. For example, toluene in the presence of KMNO4 slash KOH and second is H positive ion give rise to benzoic acid. Third is hydrolysis of nitrile. Hydrolysis of nitrile with an aqueous acid or alkaline is an important method of preparing carboxylic acid. For example, nitrile plus 2H2O give rise to carboxylic acid plus ammonia. For example, propionitrile plus 2H2O plus HCl give rise to propionic acid plus NH4Cl, or phenyl acetonitrile plus H2SO4 give rise to phenyl acetic acid plus NH4HSO4. Aliphatic nitrile can be themselves readily obtained by treatment of alkyl halide with sodium cyanide. Therefore, formation of nitrile followed by its hydrolysis affords a useful method for preparing a carboxylic acid containing one carbon atom more than was present in the starting alkyl halide. Aromatic nitrile, it may be noted, are obtained from diazonium salt as discussed later in chapter 11 and not by the reaction of an aryl halide with NaCN. Mechanism. Acidic hydrolysis of nitrile take place as follows. Firstly, the triple bond of cyanide attack on the H positive ion give rise to R single bond C positive double bond NH. Then water in which oxygen containing lone pair attack on the carbon containing positive charge to form R single bond carbon double bond NH with carbon attached a water molecule with O positive charge on the oxygen. Then oxygen take electron from the one of the hydrogen atom NH positive ion losses give rise to RC double bond R single bond carbon double bond NH2 positive and single bond OH. Then oxygen share its lone pair to the carbon single bond OH groups and the nitrogen takes away electron from the carbon double bond nitrogen and a resonance structure is obtained. Alkaline hydrolysis of nitrile proceeded as follows. Fourth is hydrolysis of acid derivatives such as acid chloride, anhydride, ester, and amide. The acid derivative mentioned above can be hydrolysis to produce carboxylic acid with varying degrees of difficulty, while acid chloride and acid anhydride are hydrolysis with water as such. Hydrolysis of ester and amide is carried out in the presence of mineral acid or alkanes. Acid chloride plus H2O give rise to carboxylic acid plus HCl. Acid amide plus H2O give rise to two molecules of carboxylic acid. Ester plus H2O in the presence of H positive ion give rise to carboxylic acid plus R-OH, and in the presence of OH negative ion give rise to oxalate ion Carboxylic ion plus R dash OH. Amide plus H2O in the presence of H positive ion give rise to carboxylic acid plus NH4 positive, and in the presence of OH negative ion give rise to RC double bond O negative plus NH3. As a practical method of preparing carboxylic acid, hydrolysis of acid derivative is seldom used because acid derivatives themselves are very often prepared from acid. However, hydrolysis of two naturally occurring classes of acid derivative, oil, fats, and protein, is employed for the preparation of certain acid. Mechanism. The mechanism of acidic and alkaline hydrolysis of acid derivative is discussed later in chapter 6. Carbonation of Grignard reagent. Carboxylic acid may be prepared by the reaction of Grignard reagent with carbon dioxide followed by decomposition of addition product with dilute mineral acid. The reaction is often referred to as carbonation of Grignard reagent. Carbon dioxide may be employed either in the gaseous form or preferably in the form of solid ice. Grignard reagent plus CO2 in the presence of ether give rise to addition product, and in the presence of H3O positive ion give rise to carboxylic acid. Mechanism. The mechanism of addition of Grignard reagent to carbon dioxide is similar to that of the addition to aldehyde and ketone. The nucleophilic organic group of the carbon Grignard reagent adds to the electrophilic carbon of carbon dioxide, while the MgX part goes to one of the oxygen. For example, RMgX plus CO2 give rise to RC double bond O single bond OMgX in the presence of H3O positive ion give rise to carboxylic acid. Like the nitrile reaction, Grignard reaction also yield a carboxylic acid containing one carbon atom more than the alkyl halide with which Grignard reagent is obtained. Organolithium compound can also be used in the place of Grignard reagent in the synthesis of carboxylic acid. Malanoic acid or and acetoacetic ester synthesis. Mono or dialkyl derivative of acetic acid can be easily obtained by malonic ester or acetoacetic ester synthesis as described below. Malonic ester synthesis. Diethyl malanoate, generally referred to as malanoic ester, form its sodium salt on reaction with metallic sodium or sodium methoxide. The sodium salt in turn can easily alkylated on treatment with alkyl halide to form alkyl derivative of malanoic ester. Malanoic ester in the presence of C2H5O negative and Na positive give rise to sodium malanoic ester in the presence of RX give rise to alkyl malanoic ester. Alkyl malanoic ester can be similarly converted into dialkyl malanoic ester. The mono or dialkyl derivative of malanoic ester may be hydrolyzed to form mono or dialkyl derivative of malanoic ester acid. These acid in turn can be decarboxylated by heating the yield mono or dialkyl derivative of acetic acid. A proper choice of alkyl halide or halide to get the alkyl or dialkyl malonic ester can be helped to obtain practically even acid by means of malonic ester synthesis. For example, let us say that it is desired to prepare N-valeric acid. This acid may be regarded as N-propyl derivative of acetic acid. Therefore, we should first convert sodium malonic ester into N-propyl malonic ester by reaction with N-propyl halide and subsequently hydrolysis and decarboxylate the alkyl derivative to get the desired product as shown ahead. For example, sodium malonic ester in the presence of CH3CH2 CH2Br give rise to N-propyl malonic ester, and in the presence of 2 moles of NaOH give rise to CH3CH2 CH2CH bracket C double bond O sodium 2 in the presence of 2 molecules of HCl give rise to CH3CH2 CH2CH C double bond OH 2 moles heat give rise to N-valeric acid plus CO2. Acetoacetic synthesis like malonic ester, acetoacetic ester can also be converted into mono and dialkyl derivative of acetic acid. Monoalkyl derivative of acetic acid ester on acids hydrolysis yield a molecule of acetic acid and molecule of alkyl acetic acid. Similarly, dialkyl derivative yield a molecule of dialkyl acetic acid and a molecule of acetic acid. For example, N-valeric acid, which can be regarded as N-propyl derivative of acetic acid, may be prepared as follows. Similarly, 2-methyl butanoic acid may be obtained by converting acetoacetic ester into its methyl-ethyl derivative followed by acid hydrolysis. Hydrolysis of trihalogen derivative. Trihalogen derivative having all the 3 halogen atom attached to the same carbon atom give carboxylic acid on hydrolysis with an alkali. For example, trihalogen derivative in the presence of water give rise to unstable unstable intermediate which releases water molecule to give rise to carboxylic acid. For example, benzotrichloride in the presence of 3 molecule of KOH give rise to benzene containing carbon having 3 moles of OH group attached to it. Then it loses the water and form carboxylic acid, and in the presence of again KOH molecule loses water give rise to potassium salt of carboxylic acid, which on further reaction with HCl give rise to benzoic acid plus KCl. Eighth is oxidation of methyl ketone haloform reaction. When treated with sodium hypohalite, methyl ketones are oxidized to sodium salts of carboxylic acid. These salts are acidified to get the carboxylic acid. For example, 2-pentanone in the presence of 3 moles of NaOI give rise to CH3, CH2, CH2, C double bond O negative, Na positive, and in the presence of dilute HCl give rise to butanoic acid. It may be seen that the acid obtained contains one carbon atom less than the starting ketone. Ninth is ant estrate homologation. This is a convenient method of homologation of an acid. It means conversion of a given acid into its next higher homology. In this method, the acid is first converted into acid chloride by treatment with SOCl. The acid chloride is treated with diazomethane to get a diazoketones. When heated with silver, the diazoketone undergo Wolff rearrangement to form a ketone. This ketone on hydrolysis gives the next higher homology of the acid. The reaction sequence may be shown as follows. Starting acid in the presence of SOCl give rise to acid chloride, and in the presence of CH2 NH2 give rise to diazoketone, and in the presence of silver and heat give rise to ketene. In the presence of water molecule give rise to higher homology. First is from alkoxide. Sodium alkoxide react with the carbon monoxide under high pressure to form sodium salt of carboxylic acid. They seal the free acid on acidification with a dilute mineral acid. Sodium alkoxide plus CO give rise in the presence of heat and pressure give rise to high pressure RC double bond O negative sodium positive, and in the presence of dilute HCl give rise to carboxylic acid plus NaCl. For example, sodium methoxide plus CO give rise to CH3C double bond O single bond O negative Na positive, and in the presence of dilute HCl give rise to ethanoic acid plus NaCl. Second is from alkene. This method consists in heating an alkene with carbon monoxide and then steam under pressure at 573 to 673 Kelvin in the presence of phosphoric acid catalyst. For example, ethene plus CO plus H2O in the presence of H3PO4 573 to 673 Kelvin temperature and pressure give rise to propanoic acid. This reaction involves carbohydroxylation of alkene, and it is also known as Koch reaction. Note: in addition to the method of preparation of carboxylic acid described above, these acids can also be obtained by oxidation of ketone by Baeyer-Villiger reaction. Physical properties. First is physical state. The lower aliphatic acids such as formic acid, acetic acid, and propanoic acid are colorless liquid having sharp, irritating smell. The acid from C4C9 are colorless oily liquid having somewhat unpleasant smell, but the higher member are colorless waxy solid having practically no smell. Aromatic acid who exist as colorless solid. Second is solubility. The aliphatic acid up to C4 are soluble in water, but the solubility falls off rapidly with increasing molecular weight as higher acid are practically insoluble in water. Amongst the aromatic acid, even the simplest acid, benzoic acid, is only sparingly soluble in water. However, the carboxylic acid are generally soluble in solvents like ether alcohol and benzene. The water solubility of lower aliphatic acid is due to their formation of hydrogen bond with water in aqueous solution. In higher acid, the size of the non-polar alkyl group become large, and the possibility of hydrogen bond formation with water decreases. Formic acid and acetic acid act as a good solvent for the salt because they have high dipole moment and can interact with cation and anion. Third is boiling point. Carboxylic acid form intermolecular hydrogen bond and therefore exist in the form of associate molecule. As such, carboxylic acid have high boiling point. The boiling point are considerably higher than those of the alcohol of comparable molecular weight. For instance, acetic acid boils at 391 Kelvin where N-propyl acid boils at 370 Kelvin. This can be attributed to two reasons. First is the OH bond in carboxyl groups is more polarized because the presence of electron attracting carbonyl group in the adjacent position. Therefore, carboxylic acid forms stronger hydrogen bond. Second is negatively polarized oxygen of carbonyl group can also form hydrogen bond with a positively polarized hydrogen of the other molecule. Therefore, majority of carboxylic acid exists as cyclic dimer held not by one but two hydrogen bond as shown below. Fourth is melting point. The melting point of aliphatic carboxylic acid do not follow a regular pattern. With the increase in molecular size, it is observed that for acid containing up to 10 carbon atom, the melting point of acid containing even number of carbon atom are higher than those of the immediately lower as well as immediately higher homologous containing odd number of carbon atom. This is called oscillation or alternation effect. For example, the melting point of butyric acid is higher than that of the propanoic acid as well as that of the valeric acid. This is because the acid containing even number of carbon atoms have carboxyl and terminal methyl groups on the opposite side of zigzag carbon chain. As a result, they fit in closely together in the crystal structure. On the other hand, acid having odd number of carbon atoms have the carboxyl and methyl group on the same sides of zigzag chain. As a result, they do not fit so well in the crystal structure. The net result is that the energy required to break the crystal structure and thus melt the acid is more in case of the acid having even number of carbon atom. Even number of carbon atom fit better in crystal structure have high melting point, whereas odd number of carbon atom do not fit so well in the crystal lattice have low melting point. The melting point of aromatic acids are generally higher than those of the aliphatic acid of comparable molecular weight. This may be due to the reason that the planar benzene ring in aromatic acid can fit in more closely in the crystal structure than zigzag chains in aliphatic acid. Chemical properties. The chemistry of carboxylic acid is governed by the presence of carboxyl group in their molecule, as this group may be further looked up as consisting of a carbonyl group and a hydroxyl group. It may be expected to exhibit the reaction of both these groups. But as we shall see, the carbonyl part of the carboxyl group does not undergo its usual reaction with the nucleophilic reagent. However, it does not influence the behavior of hydroxyl group and it is responsible for the acidic nature of hydrogen. The important reaction of carboxylic acid are discussed as follows. The reaction due to the ionization hydrogen cleavage of OH bond. First is acidity. All carboxylic acid ionized in the aqueous solution and exist in equilibrium with the carboxylate anion and the hydronium ion, thus exhibit considerable acidic character. For example, R C double bond OH plus H2 equilibrium give rise to R C double bond OO negative plus H3O positive. This cause of acidic nature of carboxylic acid have been already explained. The acidity contains of different carboxylic acid and the effect of substituent on the acidity are discussed later in section 7.7 and 7.8. Salt formation. Carboxylic acid are attacked by strongly electropositive metals such as sodium, potassium and zinc to form their salt and liberated hydrogen. For example, acetic acid plus zinc give rise to zinc acetate. They also react with bases such as hydroxide, metallic oxide, and bicarbonate to form salt. For example, RC double bond OOH plus NaOH give rise to sodium carboxylate plus H2, and 2 moles of RC double bond OH plus HGO give rise to RC double bond OO. 2 moles give Hg plus H2. It may be noted, however, that carboxylic acid are much weaker than mineral acid like hydrochloric acid, sulfuric acid, nitric acid. Therefore, the salt of carboxylic acid are readily decomposed by treatment with the mineral acid to regenerate the carboxylic acid. For example, RC double bond OO negative, sodium positive plus HCl give rise to carboxylic acid plus NaCl. Reaction involving replacement of hydroxyl group, formation of functional derivative. The OH part of the acid can be replaced by a number of groups such as chloro, OR, NH2 and OOCr- to form acid chloride, ester amide and anhydride, which are collectively known as functional derivative of acid. Third is formation of ester when heated with alcohol in the presence of strong mineral acids such as HCl or H2SO4 or as lavish acids such as PF3 carboxylic acid form ester. The reaction is reversible in nature and is also known as esterification. For example, carboxylic acid plus HCl give rise to ester plus H2O. For example, acetic acid plus ethyl alcohol in the presence of H positive ion give rise to ethyl acetate plus water. The equilibrium in the esterification reaction can be pushed in the forward direction by using one of the reactant in large excess. It is usually the alcohol which is taken in excess. The forward reaction can be further derived to completion if water formed. The reaction is removed simultaneously. This is generally achieved by using a specially designed device known as Dean-Stark apparatus. When the reaction between a carboxylic acid and an alcohol to form an ester is carried out in the presence of HCl, it is often called Fischer-Spire esterification. Relative reactivities of acid and alcohol. The process of esterification is very difficult to carry out if the acid or alcohol used in the reaction carry alkyl group near the carboxyl group or OH group. This is because the steric hindrance caused by such groups. This is very difficult to bring about an esterification reaction involving a tertiary alcohol. The order of reactivity of alcohol in esterification reaction being primary, secondary, and tertiary. Similarly, acid containing alkyl groups such as 2,2-dimethylpropanoic acid are very difficult to esterify. In fact, special methods have to be employed for the getting the ester in such cases. The mechanism of the reaction has already been discussed in chapter 1. Fourth is formation of acid chloride. On treatment with phosphorus pentachloride, phosphorus trichloride or thionyl chloride, hydroxyl group of carboxylic acid is replaced by chlorine to form acid chloride. Mechanism. The reaction involves nucleophilic attack of carboxyl group on the phosphorus atom or sulfuric atom. At the same time, molecule of HCl is eliminated. The product thus form undergo internal nucleophilic attack of chlorine ion on the carbonyl group to yield the final product. In actual practice, thionyl chloride is preferred to PCl5 or PCl3 since the byproduct of its reaction are gaseous which escape from the reaction mixture. Acid chloride form can be easily separated from the unreacted thionyl chloride by fractional distillation. For example, butyric acid plus thionyl chloride give rise to butyryl chloride plus SO2 which is gas and plus HCl which is also a gas. Fifth is formation of amide. When treated with ammonia, acid form ammonium as salt, which on heating lose a molecule of water to form amide. For example, benzoic acid give rise to ammonium benzenoids and on further heating give rise to benzamide. Formation of anhydride when treated with acid chloride in the presence of pyridine carboxylic acid form the corresponding anhydride. For example, carboxylic acid plus acid chloride plus pyridine give rise to acid anhydride plus pyridine hydrochloride. For example, acetic acid plus acetyl chloride plus pyridine give rise to acetic anhydride plus pyridine hydrochloride. Mechanism. The reaction is believed to take place by the nucleophilic attack of oxygen of carboxylic acid on the acyl carbon of acyl chloride as shown below. Reaction of the carboxylic group. Carboxylic acid do not undergo addition of nucleophilic reagents such as hydroxylamine and hydrazine to the carbonyl carbon atom of carboxylic group. This is because the attacking nucleophile, which is naturally a base, preferentially accept the acidic hydrogen of the acid, thus leading to the formation of carboxylate anion. The carboxylate anion, due to its negative charge and large resonance stabilization, resists the addition of the second molecule of attacking nucleophile reagent. As such, the carbonyl group of carboxylic acid does not form an oxamine, a hydrazone, or a semi-carbazone. The only important reaction of carbonyl part of carboxylic group is its reduction to CH2 as described below. Seventh is reduction. Carboxylic acid are resistant to catalytic hydrogenation. However, they can be reduced by lithium aluminium hydride to form primary alcohol. The carbonyl part of carboxylic group getting reduced to CH2. Carboxylic acid in the presence of LiLH4 give rise to primary alcohol. The reduction proceeds via the formation of an alkoxide which yield the alcohol on hydrolysis. For example, uric acid easily obtained by hydrolysis of coconut oil in the presence of 3 moles of LiLH4 give rise to C11H23 CH2O 4 AlLi plus 2 moles of LiLO2 plus 4H2. On further reaction with H2O give rise to lauryl alcohol plus LiOH plus AlOH3. The above method is employed for the preparation of alcohol from acid which are readily available from the natural sources. Mechanism. The reaction involves a nucleophilic attack by the hydride NH negative on carbonyl carbon. The carboxylic acid is reduced initially to aldehyde and finally to primary alcohol as shown ahead. The reduction of acid can also be brought by first converting the acid into ester, which is then conventionally reduced to the alcohol. Bovild-Blanc reduction. Carboxylic acid in the presence of R-OH, H positive ion give rise to ester, and in the presence of sodium C2H5OH give rise to RCH2OH plus ROH. Elimination of carboxyl group. It is possible to eliminate the carboxyl group from an acid to form different product as illustrated by the following reaction. Eighth is decarboxylation. Simple carboxylic acid get decarboxylated to form hydrocarbon when their sodium salt are heated with soda lime NaOH plus CO. For example, sodium benzenoate plus NaOH in the presence of CaO give rise to benzene plus Na2CO3. Mechanism: the reaction takes place through the loss of a molecule of carbon dioxide from carboxylate anion to form a carbon ion. Once formed, carbon ion get protonated to form the hydrocarbon. Effect of substituent on decarboxylation: since formation of carbon ion is the key step in the reaction, on any factor which increase the stability of carbon ion should increase the ease of decarboxylation. Therefore, carboxylic acid containing electron withdrawing groups such as NO2, CH3CO get decarboxylated just by heating alone. For example, acetoacetic acid in the presence of heat give rise to acetone plus CO2. Similarly, dicarboxylic acid containing the two carboxylic group attached to the same carbon atom are readily decarboxylated. For example, malonic acid in the presence of heat give rise to acetic acid plus CO2. Therefore, decarboxylation of suitably substituted carboxylic acids such as beta-keto acid and malonic acid constitute an important reaction of preparative interest. Ninth is Cole's electrolytic reaction. Electrolytic decarboxylation: alkali salt of carboxylic acid on electrolysis get decarboxylated to form the hydrocarbon. For example, 2 moles of Rc double bond O negative Na positive give rise to 2 moles of Rc double bond O negative plus 2 moles of sodium, and 2 moles of H2 give rise to 2 moles of H positive ion plus 2 moles of OH negative ion. At anode, 2 moles of Rc double bond O negative loses 2 electron and form an unstable compound which further on reaction gives alkane plus 2 CO2. And at the cathode, 2 moles of H positive ion loses electron to form H2 gas. It may be recalled that in aqueous solution it is H positive ion which get discharged at the cathode while sodium ion remain in the solution. The overall Cole's reaction may be represented as 2 moles of Rc double bond O negative plus sodium positive plus 2H2O on electrolysis gives alkane plus 2 moles of CO2 plus H2 plus 2 moles of NaOH. Electrolysis of sodium formate, however, yield only hydrogen and not a hydrocarbon. Tenth is distillation of calcium salt of acid. When distilled in the absence of air, calcium salt of acid yield different product as given below. First is distillation of calcium formate yield formaldehyde. Calcium formate on reaction give rise to formaldehyde plus CaCO3. Second is distillation of a mixture of calcium salt of formic acid and calcium salt of another carboxylic acid gives an aldehyde other than formaldehyde. Third is distillation of calcium salt of an acid other than formic acid gives a ketone. And 11th, decarboxylative halogenation Hunts-Dicker reactions. The silver salt of carboxylic acid react with bromine or iodine in dry carbon tetrachloride to form an alkyl bromide or iodide with the loss of carbon dioxide. For example, silver salt plus Br2 in the presence of CCl4 give rise to alkyl bromide plus AgBr plus CO2. Mechanism: the reaction takes place by free radical chain mechanism as follows. Reaction of the alkyl or aryl group. 12th, hallucination of alkyl group in the presence of small amount of red phosphorus. The alpha hydrogen atom of alkyl group of aliphatic acid can be replaced by chlorine or bromine to form the halo acid. This is known as Hall-Volhard, Jelensky, or simply HVZ reaction. For example, propanoic acid in the presence of Br2 phosphorus give rise to alpha bromopropanoic acid, and in the presence of Br2 phosphorus give rise to alpha alpha dibromopropanoic acid. It may be noted that bromination that take place exclusively at the alpha position and the reaction stops after all the alpha hydrogen have been displaced, but chlorination can continue further in the chain after the displacement of halogen alpha hydrogen atom. The reaction is believed to take place as follows: 2 phosphorus plus 3 moles of X2 give rise to 2 moles of PX3, and carboxylic acid will alpha hydrogen plus PX3 give rise to acid halide plus H3PO3. Aromatic substitution. Aromatic carboxylic acid can undergo the usual electrophilic substitution reaction of benzene rings such as halogenation, nitration, and sulfonation. It may be recalled that the carboxylic group is a meta-directing and deactivating group, and therefore the above reaction takes place only under vigorous condition. For example, benzoic acid in the presence of fuming H2SO4 and heat give rise to metasulfonic benzoic acid. In the presence of HNO3, H2SO4 heat give rise to meta-nitrobenzoic acid, and in the presence of Cl2, FeCl3 give rise to metachlorobenzoic acid. It have been studied in earlier classes that the carboxylic group attached to the benzene ring exert an electron withdrawing resonance effect minus R effect and also electron withdrawing inductive effect minus I effect. As a result, such stability of carbocation intermediate formed during electrophilic substitution is decreased, particularly at ortho and para position, and consecutively, electrophilic substitution does not take place easily. Special reaction of formic acid. In the molecule of formic acid, the carbonyl group is attached to the free hydrogen atom. Therefore, formic acid combines the properties of an acid and an aldehyde as required by the structure. Therefore, it undergoes certain reaction not given by other carboxylic acid. The important reaction of this type are oxidation. First is oxidation. Unlike other acid, but like aldehyde, formaldehyde is readily oxidized to carbon dioxide and water. Therefore, it reduces Tollens reagent to form a silver mirror and Falling solution to form a red precipitate of CO2. For example, H formaldehyde, formic acid, formic acid plus Tollens reagent give rise to 2 moles of, in the presence of 2 moles of OH negative ion give rise to CO2 plus 2 moles of H2 plus 2 moles of silver mirror plus 4 moles of NH3, and Falling solution in the presence of Falling solution give rise to CO2 plus 3 moles of H2O plus red PPT of copper 2O. Formic acid also reduces acidified potassium permanganate, acidified potassium dichromate, and mercury chloride. For example, 5 moles of formic acid plus 2 moles of potassium permanganate plus 3 moles of H2SO4 give rise to K2SO4 plus 2MnSO4 plus 8H2O plus 5CO2. And formic acid plus 2 moles of HgCl2 give rise to white PPT of Hg2Cl2 plus 2 moles of HgHCl plus 2 CO2. Reaction with concentrated H2SO4. When heated with concentrated H2SO4, formic acid gives CO2 plus H2O. Action of heat on sodium formate. On heating to 663 to 673 Kelvin, sodium formate gives sodium oxalate and hydrogen. Acidity constant of carboxylic acid. It have been already pointed out that in aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate anion and the hydronium ion, that is Rc double bond OH plus H2O give rise to Rc double bond O negative plus H3O positive. According to the law of mass action, the equilibrium constant Kc can be expressed by the following expression: Kc is equals to bracket Rc double bond O negative bracket close bracket start H3O positive bracket close divided by carboxylic acid and water molecule. Since water is taken in large excess and its concentration remains practically constant, so H2O can be omitted from the above expression, and the relationship can be written as Ka is equals to Rc double bond O negative H3O positive and Rc double bond OH. The equilibrium constant K is generally referred to as the acidity constant. Since K is directly proportional to the concentration of H3O positive ion, it would have low value in case of weak acid and high value for the strong acid. In other words, the value of K reflects the acidic strength or the acidity of the acid, and therefore K can be used for comparing the strength of the different acid as compared to the mineral acids such as HCl, HNO3, and H2SO4, which have Ka value of the order of 10 to power 7 to 10 to power 9. Carboxylic acid have Ka value of the order 10 to power minus 4 to 10 to power minus 5. Thus, carboxylic acid are much weaker acid than mineral acid. pKa value. These days, the acidic strength of an acid is also represented in terms of pKa value, which is the negative logarithm of acidity constant, that is pKa is equals to minus logarithm of Ka. For example, the pKa of acetic acid is equals to 4.75. It may be noted that stronger acid has larger Ka value but smaller pKa value, while the weaker acid has smaller Ka value but larger pKa value. Most of the simple unsubstituted carboxylic acid are of moderate strength, having pKa value of about 3 to 5. pKa value of some of the acid are listed in table 5.3 given on 5.24 page. Effect of substituent on the acidity of carboxylic acid. The position of the equilibrium in the reaction between a carboxylic acid and water to furnish carboxylate anion and the hydronium ion depend upon the stability of the product relative to the stability of the reactant. Any factor which stabilizes the carboxylate anion more than the parent acid should increase the acidity of and any factor which destabilizes the anion should decrease the acidity. An electron withdrawing substituent Cg on the carboxylate anion attract electron toward itself and thus disperse the negative charge on the anion. As a result, it stabilizes the carboxylate anion and thus increase the acidity of the parent acid. G attract electron towards itself, disperse the negative charge on the anion and thus stabilize it, whereas G dash release electron away from itself, intensify the negative charge on an ion and thus destabilize it. An electron releasing substituent, say G dash on the carboxylate anion, intensify the negative charge of the anion and thereby destabilize the anion. Consequently, decrease the acidity of the parent acid. In short, it may be stated that electron withdrawing group increase the acidity while electron releasing group decrease the acidity of carboxylate acid. Table 5.3 shows the effect of different substituent on the acidities of aliphatic and aromatic acid. Aliphatic acid. Important conclusion. It is quite obvious from the above discussion that the stronger the electron withdrawing group present in an acid, the greater is its acidity. For example, fluoroacetic acid is stronger than chloroacetic acid because fluorine is stronger electron withdrawing than chlorine. Second is, the larger the number of electron withdrawing group present in the acid, the greater is the effect of the on the acidity. That is why we find that trichloroacetic acid is stronger than dichloroacetic acid, which is in turn is stronger than monochloric acid. Third is, as a group having electron withdrawing inductive effect moves away from the carboxylic groups, its effect on the acidity become less pronounced. This is quite in keeping with the fact that inductive effect falls off rapidly with the distance. This is why gamma chlorobutyric acid is weaker than beta chlorobutyric acid, which in turn is weaker than alpha chlorobutyric acid. Fourth is the effect of electron releasing group is shown in section D of the table. It is apparent that acetic acid is weaker than formic acid because it contains an electron releasing CH3 group attached to the carboxylic group, which while formic acid has only hydrogen attached to the carboxylic group. Aromatic acids. First is benzoic acid. In discussing the acidity of aromatic acid, let us begin with benzoic acid, which is the simplest acid containing a carboxylic group attached to an unstable, unsubstituted benzene ring. It means benzene C double bond OH. Phenyl group directly attached to the carboxylic group exert an electron withdrawing inductive effect minus I effect, but at the same time it tends to release electron towards the carboxylic group due to the resonance effect. Now the plus R effect of in this case is more dominating than minus I effect, so that phenyl group has a net electron releasing effect. That is why benzoic acid is a weaker acid than the formic acid. It may be noted, however, that the net electron releasing effect of phenyl group in benzoic acid is lesser than the electron releasing inductive effect of alkyl group present in aliphatic acid. Therefore, benzoic acid is a stronger acid than aliphatic acid from acetic acid onward. Phenyl acetic acid. Let us now consider the simplest aromatic containing the carboxylic group in the side chain phenylacetic acid. Here, resonance effect is not possible due to intervening carbon atom between the phenyl and carboxyl group. Therefore, phenyl group exert weakly electron withdrawing inductive effect. Consecutively, phenyl acetic acid is stronger acid than acetic acid and higher aliphatic acid containing electron releasing alkyl group. It may be noted that even though phenyl group have electron withdrawing inductive effect, benzyl group, which may be treated as phenyl substituted methyl group, have electron releasing inductive effect. As such, phenyl acetic acid is a weaker acid than formic acid. At the same time, electron releasing effect of benzyl group is more than the overall electron releasing effect of phenyl group. Hence, phenylacetic acid is weaker than even benzoic acid. Effect of substituent on acidic strength of aromatic acid. The effect of substituent group present on the benzene ring on the acidic strength of aromatic carboxylic acid depend upon both the inductive and resonance effect operating when the group is present in different position as illustrated below. First is group having electron withdrawing inductive effect as well as electron withdrawing resonance effect such as NO2 group. Let us consider the effect of presence of nitro group on the benzene ring on the acidities of aromatic acid. Nitro group exert an electron withdrawing inductive effect as well as electron withdrawing resonance effect. However, it may be recalled that resonance effect operates only in ortho and para position, there being hardly any effect on the meta position. This means by resonance mechanism, the nitro group cannot markedly reduce the electron density at the meta position, although it can reduce the electron density at ortho and para position. At the same time, it can reduce the electron density at all position by inductive mechanism. The net result is that it exerts greater electron withdrawing influence when present in ortho and para position and greatly stabilize the corresponding carboxylate anion. That is why ortho or para nitrobenzene benzoic acid have greater acidity than meta nitrobenzoic acid, which however has greater acidity than benzoic acid. The overall odor is ortho nitrobenzoic acid. Para-nitrobenzoic acid, meta-nitrobenzoic acid, and benzoic acid. Effect of halogen. Halogen has electron withdrawing inductive effect and electron releasing resonance effect, but the inductive effect is stronger than resonance effect. To understand the effect of the presence of halogen on the acidity of aromatic acid, let us take up the case of para and meta-chlorobenzoic acid. When chlorine is present in para position, its electron withdrawing inductive effect is opposed by its electron releasing resonance effect. However, since the inductive effect is stronger than resonance effect, overall effect is electron withdrawing so that the carboxylate anion gets stabilized. As a result, para-chlorobenzoic acid is stronger than benzoic acid. When, when chlorine is present in meta position, only its electron withdrawing inductive effect operates since it is hardly any resonance effect operating at meta position. As such, there is a strong electron withdrawing effect so that carboxylate anion is much more stabilized than in case of the its isomer. Hence, metachlorobenzoic acid is even stronger than parachlorobenzoic acid. Orthochlorobenzoic acid is found to be stronger than both meta and para isomeric due to ortho effect. Thus, the overall order of stable acidity of chlorobenzoic acid is orthochlorobenzoic acid, metachlorobenzoic acid, parachlorobenzoic acid, and benzoic acid. Third is group having electron withdrawing inductive effect and electron releasing resonance effect, but resonance effect is stronger than inductive effect such as OCH3 and OH group. For example, let us now consider the effect of hydroxy group when present in meta and para position respectively in the hydroxybenzoic acid. Hydroxy group has the electron withdrawing inductive effect but an electron releasing resonance effect, and its overall effect may be explained as follows. Due to its electron withdrawing inductive effect, it tends to decrease the electron density at all position, but at the same time it tends to increase the electron density at para position due to resonance mechanism. While the meta position is not markedly affected, since the resonance effect is more powerful than the inductive effect, the net result is there is an increase in electron density at para position. On the other hand, only electron withdrawing inductive effect operates at meta position so that there is a decrease in electron density at meta position. Thus, the hydroxy group present in para-hydroxybenzoic acid exert an overall electron releasing effect and destabilizing effect on the carboxylate anion so that para-hydroxybenzoic acid is weaker than benzoic acid. But in case of meta-hydroxybenzoic acid, hydroxyl group exert an electron withdrawing and stabilizing influence on the anion, and as much as hydroxybenzoic acid is stronger than benzoic acid. Meta-hydroxybenzoic acid is stronger than benzoic acid than para-hydroxybenzoic acid. The observed order of methoxybenzoic acid is also similar. These group having an electron releasing inductive effect such as CH3, CH2, CH3 group. Such groups have acidic weakening effect when present in para and meta position, but the effect is relatively more in meta position. Therefore, the order of acidic strength is benzoic acid, metabenzoic acid, and parabenzoic acid. Exception behavior ortho effect. An unusual observation is that particularly all group and attached ortho to carboxyl group in aromatic acid increase the acidity. This anomalous behavior of group when present in ortho position is known as ortho effect. However, it has not yet been possible to explain this behavior completely. The acidity of some simple and substituted aromatic acid are given in section E of table 7.3. Test of carboxylic acid. Carboxylic acid can be detected by following tests. First is carboxylic acid turns blue litmus red. Second is they give effervescence with the liberation of CO2 when added to a solution of sodium bicarbonate. Third is when a carboxylic acid is heated with alcohol in the presence of small quantity of concentrated sulfuric acid. A pleasant smell is produced due to the formation of an ester. Thank you.